Can you see the screen?
Yes, sir.
Okay. Okay, so we are discussing about how to create shared memory using system calls, or what are the system calls available to create a shared resource, and how to use it among multiple processes. So what we found, there are four possible, at least four important functions, or I mean system calls, through which you can create and use shared resources. And these are the four calls: shm get, shm at, shm dt, and shm control. And control operations that can be possible, but in the example that I have shown, is to destroy an existing shared resource. So there are other possible control operations also. And in this, so I tried to illustrate using that example in my last class. So in this class, I'll show it running a piece of code and see that how it works. And also I'll talk about some of the commands in the shell through which we can see the existence of the shared memory, and we can see how many processes are at a particular point of time using it. Okay, so can you hear me? Hello, because the screen is gone.
Yes, sir.
Hello. Okay, fine. So as you can see, this blue box, it contains in this control uh, statement, in the control system call, you can see the third argument, which is a pointer to this structure. So structure is structure shmid underscore ds. So this is the shared memory data structure that Linux stores. Okay, and this has got this number of details. So the first thing is the operations that is permissible, or that is permitted. So this will include the permissions. In our case, I have in the example we have shown it 666. That means the shared resource or memory that we create can be read, executed, and also written, modified. Then it is a segment size, the number of bytes that it will include. Then it is the last attach time, because there can be multiple processes which may need to attach, and within a process you may, during the process lifetime, you may attach, you may detach, again you may attach and detach. So there can be multiple number of times a particular process can detach or attach to a existing shared resource, and that can be done by multiple processes also. So this single data structure holds this the information corresponding to a particular shared resource type, and this also the last time that is detached, and the last time that it has been changed, because multiple processes can write on it also. So the last time it has been modified, and the PID of the creator. So if there are two processes, we found that one process may physically create it, and the other process may call shm get to just get the local ID instead of physical creation. Okay, so the ID of the creator and PID of the last operator, so whoever has performed some operation on it, and also the number of current attaches. So many so this also might vary, and before it gets destroyed, the number of processes which attaches to it might go on and up and down, so like that. So these details of the structure can also be, the contents of the structure can be displayed in the command line also, that we'll see. Okay, so this is um, the modifications, because there were some mistakes in the last class. So this is the refined copy of the code, and I'm not going to the details of it. So shm get is here, and then shm at, shm. So first we create it, because this has been written, then we try to attach it. So once we create, we get the local ID. This is the global ID. This is the creator process. In fact, we are running it. So in the example that I'll show, I'll run it first. So this will be the creator process, and this will be the maybe you can call it as a user process. It will just use it. And in my case, I have the creator actually creates and writes something to it, and this user just reads the contents from it. Okay, so this when the creator, after it gets created, it attaches with it. So it attaches to this shared memory, this local pointer variable, through which it can access that shared resource. Okay, and then after that it typecasts and copies it to another integer pointer x, and it modifies the contents of the first location and the second location, because it will be treated as a array of two integer elements. So, and it displays the contents like this, and finally it detaches and it exits. So the process, the creator process, when we run it, as you can see here, it it creates and attaches, and then it writes updated values, and then it exits. So once it exits, this shared piece of data, or a shared piece of memory, remains in the system. Okay, so so this creator process creates, writes something, and it itself terminates. But this shared piece of data with the first location containing 5 and the second location containing 6 will remain. And when this process is executed next, afterwards, after the termination of the previous one, then it goes on in calling shm get, and when it executes, it finds that this has already been created, it is already there, this shared piece of data identified as shm key. So in this key value, it's already there. So it just gets a local uh, id corresponding to it, and through that local id it attaches. So now this you can call it as a reader process or whatever, it uh, gets connected. So this, through this shm memory, I just use a different name, I could have used the same name here also. So through that it points to this, and once it does it, so this will be treated as a void, pointer to void. So I suitably typecast it and copy it to x, and in this case, instead of just modifying, I just read the contents of it. So the second process, it just connects to that, and it points to this sh through this shm mem, and then it typecasts and assigns it to an integer pointer, and through that it just reads the contents of the first location and the second location. So it is merely just reading the contents, and what we expect, even though this process has been terminated by that time, the reader process can retain the values that the previous process has written for it. Okay, and it goes into a for loop. So I can comment it also. So it keeps waiting, so it neither detaches nor it destroys. So those are the last two steps. So if I run it, if I compile it and run it separately, shared memory attached, so it has been created and attached, and it reads the values. So let us see that whether it so definitely it is not reading the proper value. So let us see that if it can read it properly. So here, these are the codes. This is the, is this visible, the editor?
Yes, sir.
Okay, so this is the writer process. Okay, so this is the first process that, so here it modifies. So here it modifies. So this is the writer process, and this is the reader process. Okay, so let's see how it works. So this is a shared memory create. This is the writer process, or the process which creates. In fact, there is no distinction in terms of who creates and who uses, apart from the way they use it. So I just compile it and I run it. So this says that it has been created and attached, and updated value of the shared memory is 5 and 6, but it actually exited. Okay, so if I would like to see whether it has been it's already there or not, I write IPC. This is the command IPCS hyphen m. IPCS s means it is showing the status. Okay, so as you can see in the first column, what we can see here, this is the key value, right? What is the key value? 1 2 3 4. And if you can see it here, this is hexadecimal 1 2 3 4, right? So this shared resource, it has been created by this process, and you see even though the process has been terminated here at this point, it still exists. So shared memory segments that has been created that currently exists. So this is a key, this is a shared memory ID. So this is a local ID, this is 0, the owner, the username, and the permission bits and the bytes. How many bytes do you expect? Two integers, so 4 plus 4 8, and number of attachments, number of processes which are attached to it. Right now, are there any processes which are attached to it? Hello?
No, sir.
Because the creator, it has been terminated, but the resource exists, and the resource exists with the contents of it also. Okay, so that's a nice thing. And if you look into it like this, can you see the details what it says? Shared memory ID, this UID is this, GID is this, CUID and all this. So the group ID, the user ID and all these are listed here. Then it says the mode, then the access permission, then the bytes. So all these details are given here, and this is the number of attachment, and this is so what it actually displays, it displays basically the contents of that data structure, of that structure corresponding to the shared resource that we discussed in the yellow box. Is that fine? So you can see the attachment time, the last attachment time, last detachment time, and the changes that has been made, all has been recorded. So the process which has done all these does not exist, cease to exist, but the resource remains, and some other process who is having that global key can still access it, and can read it, can write it, doesn't matter. And probably that process's task will be to destroy it also, otherwise you have to destroy it from the command line, right? So now if we execute compile the user process means the reader process. So it got attached to the existing shared resource whose global ID is 1 2 3 4, and it has read the values also. You can see that 5 and 6 has been read. Got the point? So this process read whatever the previous process written for it, and in some other window, if I check this, so is there any modification of the last access attach detach? Can you see any change?
And attached, sir.
See,
One
it was
process attached.
yeah. So attachment is one process that is there, and also the last time it got attached. So the thing is, as you can see here, so the arena that we are talking about, so arena is a shared resource that somebody created, some club created, and other clubs, they keep using it. Even the CCS program has been terminated, but later on it remains, and GNU log uses and some other uses. So this goes on, and maybe the last club who has the having the hosting the last event, their task will be to destroy it. And if it is still not destroyed, the authority will destroy it. So like the command line, it will be destroyed. Okay, so got the point? So how the two processes are communicating with each other? So this shared memory is a type of, is a way of means of inter-process communication. So through this shared piece, they are communicating, right? And if I just write this, you see number of attachment is now 1. Now you can really see that one process. Now if you have got many such user processes, we see the number of attachment keeps increasing. Okay, is that okay? So now if I remove this for and recompile it, now see what happens. So now it has not only been attached, read the value, and without waiting any further, it also, as you can see, it detaches first and then it destroys. So destroying is using SHM control. So this, if I put this flag IPC RMID, so this will ensure that the shared resource gets the shared resource having this ID. So this ID also, so this ID, who creates this ID? The operating system creates the ID when it was created for the first time using SHM get. So using the global key that is known, that is probably distributed offline, when any process executes SHM get, so through SHM get it is a process of acquiring the local key. I mean local key, or I mean the logical key that the operating system creates for it, and through that you can actually refer to it. Okay, so this global key has been assigned by the user, but the operating system provides a uh, logical ID to that shared resource, which is a fixed value, and that whoever process executes SHM get receives it, and through that it attaches and then finally detaches and all this. Okay, while destroying also this logical ID should be given, not the global ID. So the global ID, once creation, it is no longer in use, right? And this is the permission bits, and you can change it to some other permission bits, like this is not executable, so that's why I have made it 666. Now here, before you detach, or I mean before you destroy, how can you be sure that nobody else is using? Can I make some provision that the uh, process which is trying to destroy the uh, that particular shared resource need to make sure that no other processes are attached to it? Can it be done? Can you give some idea how it can be done?
Sir, in the shared memory, we keep a flag.
No flag is required, because in the shared memory data structures, you see, this data, in this data structure itself it is there, right? This data structure here, and as you can recall, what is this SHMCTL? Here you could probably pass equivalent, so you can declare a pointer to this kind of data structure, and through that you can acquire the value of it, right? So before you actually destroy, you can make a call to this SHM control and try to find out and pass the, so instead of passing 0, you can pass the pointer to a structure variable, SHM data structure, and from that you can unpack, you can refer to this value in attach, right? And from the in attach, if you find that it is just 1, that means you are the only person, so then you can safely detach it. I mean you can safely destroy it. So every process can write it, but that can have some precondition of calling SHM control first to get the entire information of that particular shared resource, and if it is not been attached by any other process except the current one, only then it will call SHM CTL, otherwise it will just destroy it. Okay, but now in this case, if the writer process does it, then the reader process will have no other idea how to do it. And in fact, if you can see here, see if I remove this IPC create, from what? From the writer process, from the reader process, and now if I compile it and run it, what do you expect? Are there any shared resource that is available right now? Are there any shared resource available in the system? Are there any available resources? No, because both the process has been terminated. Now I have compiled the writer process, and in the writer process what I did, I removed this option IPC create or IPC create. So if I remove that option, this process will be able to execute SHM get, but will not be able to create if the shared resource is not existing. So what it says, got the point? So the reader process or the second process, you have not make the provision to create a shared resource. Earlier the first process created, and that's why it can attach. Now there is no existing resource, and you are trying just to attach, just to get that local ID. So it will be a failure. But if I write this one, this one, then sorry, this or now it is working. That means even though the first process, the writer process was not there, now the second process, which is just merely the reader process, it has executed SHM get, and because it was not there, it created a fresh copy of it, attached it, and then just read the content. So the default values of that shared locations was just 0, and that's why it is showing here 00. And finally it detached and also destroyed it, and that's why there is no trace of it also. Okay, is that fine? Hello?
Yes, sir.
Yes, sir.
So do you have any questions? So the thing is, the only thing is, I mean, if you forget to delete, then you can obviously delete from outside, but you have to make provisions. So it is not that because when the writer process creates it, the maybe that the reader process is not yet been created. So and that does not mean the writer process can just destroy it now. So the thing is, whether you destroy it and who will be destroying it, that is up to you. That is up to the application that creates multiple processes, and they are using some shared piece of data to do this. Now, one possible use can be in the previous examples, we found that the parent creates multiple child processes, and the child processes earlier, they were forced to communicate only through a shared file, because if the parent creates a file, the child processes get automatic access to the file through the shared file, the file descriptor, right? So now we can have a much better way of not just creating a file, but creating a shared piece of data they can communicate. So the idea can be a parent process can create a shared, say, array or a shared variable, and it can have, say, it can have elements as many number of child processes it has got. So it gives some tasks to the child process. I mean, something like this. Okay, so here I have just mentioned those commands, how to do it. Now the thing is here, if I say that in the parent process, the parent, this is P, the P creates this shared piece of memory to be used by, say, C1, C2, C3. And in fact, the parent creates, and the parent may not attach it with also, but the parent can attach it. So maybe the parent attaches with it, each of every child process separately attaches with it. So this is the area where it has got 3 locations maybe, and this part is meant for C1, and this part is meant for C2, and this part is for exclusive modification for C3. And if there is some task given, say for example you are trying to find out the mean of all the elements in this array, mean, so you have to get the sum. So the sum of this part, so this was another array, say for example, and this array has been basically copied to different. So once a parent creates it, this child has got a copy of this array, it has got a copy of this array, and it has got a copy of the array. And this can be declared as a separate shared array also. So the point is what I want that this child will get the sum of these elements, this child will get the sum of these elements, and this child will get the sum of these elements. And once they get the sum, this child will write the sum here. PID and making the parent wait for all the child process to terminate. After the terminates, the parent can easily add these three elements and divide it by the total number of elements to get the mean of it. Sorry, the average of it. Okay, so this can be one simple exercise where the parent and the child process, they can now communicate with using shared memory. And earlier it was a difficulty that how the child process, if it has computed something, how it will pass it on to the parent. Now this is not an issue, right? So this will be a small assignment that will be using the fork child processes, and you should use the SHM get attach and all this uh, to get things synchronized and to enable the process communication among parent and child. But in this case, you should keep in mind that the child also need to execute SHM get, otherwise, and SHM get and SHM AT, otherwise it will not work. Okay. So now I switch to the uh, other topic. Other topic means other way of solving the data access synchronization problem, and where the previous case we completely we use the algorithmic approach. So in the algorithmic approach we relied on purely say logical say on our logic to get rid of the race condition and to satisfy all the say the desired conditions for the solution. And we found that it is not that always easy. So the other option is there are four options. So the second option is to use the operating system support. So the operating system provides some additional support so that the problem of data access synchronization can be resolved in a bit easier way. And that is, it provides a specific construct, a primitive called semaphore. Okay, so let us see that what a semaphore is and how it works. So before we get into the details of semaphore and how the operating system uh, provides its functionality, let me just talk about something very analogous to what semaphore is. So the idea was, let us look back uh, say several decades back. So I'm talking about the time in the mid 90s when we were studying in the colleges. We just entered in the colleges. So those days, this phone calling is a real problem, and we used to have phone calling booths, and STD was something giving a STD call means from one city to other city. If you want to make calls to Kolkata, also it was a STD call from Durgapur, and you have to really wait for maybe 8 p.m. 10 p.m. when the the call rates slashed down, and people waited for that. And so it was a real problem. So the telephone booths were something like this. So there was a handset, okay, so telephone handset, and there was also a door. I mean, in that, so this is a booth, telephone booth. And the idea was, so how can we automate the whole thing? So some person, he has got a telephone booth, okay, so he wants to automate it. So he expects that even he is not there, the customers come and they will operate and they will pay it and they will leave, and there should not be any chaos, any kind of chaos that should take place. So this is a door, and the thing is, to make the proper provision, what he did, so instead of a door he actually used a I mean, it was just a kind of analogy that I'm drawing. So he just used a light, okay, lighting arrangement. So the thing is that when the first person comes, you should just see and the thing is, the lights are blinking, lights are glowing. So if the first customer comes, he sees the lights are on. So the lights are on means nobody is there in the booth. So what he should do, he should enter and start making the phone call. But so he starts making the phone call, but before he makes the phone call, what he should do now with the light, so that to stop other customers to also enter into the booth and interfere?
Turn it off, sir.
Turn it off. Okay, so a simple case. So he just turns it off, and maybe there is a switch, small switch here, which goes here, and from the inside if you press it, it will be on, and from outside if you press it, it will be off. So it will be off from inside, and if you press it from outside, it goes to the same and it will be on, so something like that. So in fact those arrangements can be made quite easily. Okay, so that is the case. So when he was calling, and in fact this was off, so the light is off, right? Say for example this was off, one person is making a phone call and the other person came. What do you expect that the second customer to do?
Wait.
He should wait, but he should wait, and probably you want the customers to be very happy, to be happy while they are waiting. So what you make the provision, you have a nice sofa kind of thing, and the customer can, he can simply sit and relax, and he can simply start sleeping also. So those days were not the case that you will be busy browsing your smartphones, because and it's really difficult to pass on your own time. So they can simply sleep. Okay, because you really don't know how long this person who is inside will continue, because you have enough money, so he will continue for 1 hour also, and maybe paying say, something around 30-40 rupees. So any other person comes, they will simply join, and they will simply, so the thing is, when they are in the sofa, they are simply relaxing. So relaxing has got some specific connection with the way we deal with processes. So they are not actually busy looking whether he has finished or not. So they're simply relaxing. So they don't care about. So it's not busy waiting. So they're waiting, but they are simply, it's something like suspended. So they are not actually engaged in knowing that whether the existing customer is down or not. So they can simply relax. Okay, so now what happens when the person leaves, this person leaves, what happens, what do you expect?
Now
When
another
this
person will go to the booth.
so what will be the mechanism? So the first thing is, he will first check, because it says the door is not there, so he will see that if there are some persons waiting in the sofa, what he will do?
So we'll
Turn
turn
on
off
the
the
light.
light.
Basically, so no, he will not turn off the light. If he turns on the light, then these persons are sleeping, so they are not aware of what is there. So rather, there is a calling bell kind of thing. Okay, so there is another switch. He will press the bell. So there is a bell. Bell will ring. Okay, so when the bell rings, they will all wake up, and the first person will get an entry, right? And if this person finds that nobody is waiting here, nobody is waiting in the sofa, what he will do, then he will press this button. This button is meant for switching this light on. So this is the on switch, and this was the off switch, right? So the off switch will be inside the booth, and the on switch is outside the booth. So before he leaves, if he finds nobody is here, he will switch on, otherwise he will press the buzzer and the bell will ring. I mean, it will be a bell that will start ringing, and they will wake up, and the first person who is in the queue you can think of, he will enter. And when he enters, he does nothing, because he just because by the time the light is anyway off, he just enters, makes a phone call. When he leaves, he does the same logic, right? So what is the critical section here? What is the critical section here? I mean, something equivalent to that. This phone booth, inside the phone booth is a critical section, right? So if I write the logic that we found here in both the cases, what I find, so if I write here the entry logic, if I entry logic is associated with wait, right? So if I call it as wait, so what is the logic that the customer performs? What is the logic here? And this whole arrangement, if I call it, say this arrangement, this is what semaphore is. The whole arrangement is semaphore. So if I say this is called S, Okay, so what is need to do? So wait is meant for the entry process. So in the entry process, what you need to check first? If what you check here, if
Sir, the light.
if the lights are on, if the lights are on, then what you do? If the lights are on, you basically switch off the light, right? You switch it off. Else what you do? Else
Sit on the sofa.
sit on the sofa and relax. And this is significant because this relaxing, that's why I specifically use the term sit on a sofa and relax. You should not just move around here and there and keep on. So we just try to avoid busy waiting, because that will anyway steal the CPU cycles and it will unnecessarily delay other processes. So there is no point of stealing the CPU cycles just to know that whether the process is done or not, the process which is currently in the critical section, right? So this is the process. And what is the other process? Before you leave, you basically execute this process called signal, right? It is also associated with S. So what is the logic that we perform now? Before you leave, once it is done, what do you do? If what it checks, if the sofa is empty, then what you do? You basically switch on the light. Else what you do?
Ring the bell, sir.
Ring the bell. So ring the bell means it is a process of it's a process of basically waking up the person from the sofa, I mean who are waiting in the sofa. And this waking up a person means which person should be awakened. Now
The
there is a
first
policy.
in sofa, sir.
Now, so this may not be the policy. So the policy, this the default policy is a FIFO. If you are maintaining a queue, it's like that, but it can be something else also. So there are mechanisms. So if I mean, so this is analogy to the semaphore. I'll come to that point. So this is what is done. So let us try to consider something very similar to, and if this happens, so the thing is this wait yes, and what you do here, then we make phone call, and then you signal. So that is what you do. Any customer trying to make phone calls in this booth, so it's completely automated phone booth, and you know that the customers are well behaved and they actually make the payments that they make. So the shop owner, he can peacefully go away and making sure that he has made the entire arrangement, and there is no chaos also. So they will also not fight among each other. So so if I say this is something analogous to a semaphore, so what are the components of the system? What are the components of the system here? What you need to have? It's a light, and what else? When the shop was initially open, what are the components you had as a part of the arrangement? Light and what?
Light, booth, bell,
Bell,
sofa.
sofa.
Yes, the
Booth,
sofa.
bell.
So these are the two things. I mean, these are the two things they need to have. Now, if you try to draw some analogy with this, so this light is on and off. So what you can have here is some Boolean variable, right? Or some integer variable, say X. And sofa is what is this? This is some Q. Okay. So these are the two things. And these together, the structure together makes it's a semaphore. Got the point? So what is a semaphore? Semaphore is not only this variable X, but it also includes this Q. So this X and Q together is a semaphore. And if I say semaphore S, and this need to be, so this S is a particular semaphore instance, right? This is a variable, say for example, of this type of structure. And this should be shared because multiple processes need to use the same semaphore for accessing for controlled access to that particular resource. So every process, every resource need to be protected using a semaphore. So what is the equivalent of wait here? Wait S. So what is the equivalent in the computing terms? What should I write? If Tell me first. Lights on. What do I check?
Sir, X is 0.
So s dot
S
s
dot
dot
S dot.
s dot x s dot x if it is equal to 0, right? If it is equal to 0, then what we do? If we switch it on,
X is
sorry,
equal to
will we check this equals to 0 or 1? What?
1, sir, 1 on.
It should be 1. It should be lighted on. Then it will be s dot, we make it s dot x equals to 0.
0.
Else what we do? Else
So we take that
s
first
dot
element
x.
of Q.
So basically now what happens? Sitting the sofa means the process need to be enqueued in that queue. Which queue? Associated with this s. So s dot q, what you do here? S dot q dot insert. You call the insert command, insert function like this. Is that fine? Oh, sorry. Is that fine? So here waiting in the sofa is equivalent to putting the process in this queue associated with the semaphore. Is that okay? Hello?
Yes, sir.
So now what is the signal operation? Signal operation on S. What is this? Equivalent if the sofa is
Q
empty.
is
So what do you
empty.
check? S dot q dot is empty. If this is empty, if it is true, then what I do? If it is empty, then I make it s dot x equals to switch on the light. Switch on the light means setting the boolean variable to 1, right?
And
And else what I do here? Else what I do? Else what is done? A process from the queue is deleted, right? Hello? Hello? Can you hear me?
yes, sir.
So this is basically unblocking one process from the queue, the first in first serve. So the thing is, so this is what semaphore is. Okay. So in fact, when we talk about semaphores, instead of wait, we better call it as a P operation, P. And the signal, we call it basically, it's a V operation. Why it is P and V? Because the semaphore, it was first proposed by Dijkstra. So Dijkstra is, as I was mentioning, Lamport, Dijkstra, they are all uh, they all contributed a lot to the development of the operating system and as a whole. Okay, so Dijkstra, he has got the shortest path algorithm. He has got many other algorithms also. So he proposed the construct of semaphore, and he was a Dutch scientist, and he used Dutch words to do this. So this P stands for proberen, and V stands for Verogen. So proberen means this is to uh, actually test. Proberen in Dutch you can try. It stands for test, and Verogen means to increment. It basically increments the value. So you can think of plus plus something like this. So now what happens? So is that fine? So what is the resource here? So now what you do here, instead of wait and this, you can say P of S and then CSR critical section and then V of S. So this is what computation it will mean. Okay, is that fine? So can you tell me what happens if we have got multiple? So now so this is restricted if you have got only one resource unit, right? If you have got only one handset, but if you have got multiple handsets, that also you may decide. So what do you do then in that case? What is the solution then? You have got say 3 handsets, so for example. So how many? So how to control the access to it? Will one light be enough for doing that?
No, sir.
So you can
No,
have
sir.
three lights. You can simply have three lights, right? Arrangement of three lights. So whenever you have got an entry, so a new person comes, so they definitely the sofa is to be there. So that is definitely there. But when a new person comes, he finds, if he finds that, what will be the logic now? If he finds any one of the light is glowing, he will then enter and it will be a off switch, right? If he presses it, one of the lights will be off. If there are three lights, then two will be glowing after it has been pressed. If one is glowing, none of them will be glowing after it has been pressed. Like it will, if you press it, you can make the arrangement. It's a very simple arrangement, circuit arrangement. So it will be switching off one of the lights. Okay, and before he leaves, he will make sure that there is another switch which will basically switch on the lights, right? It will basically switch on just one light, but it will depend on whether if this sofa is empty. If the sofa is not empty, it will rather press a bell. So it will just press the bell, and you will find that uh, the bell rings and it will alert somebody who is waiting. So can you just write it within say 2-3 minutes? Can you just write it how the wait will work here? Wait and signal. What will be the modifications here? What will you do here? If what I write, what do I write? Lights on is greater than 0. Say you can count it greater than 0, then you write lights on. You basically decrement. You basically switch off one light. Else, sorry, sit in the sofa and relax. That's all. And here, what you do while you are leaving, what you do here? If you find an empty sofa, then what you do here? Lights on. What will happen here? Hello?
Incrementation.
Just increment it. That is the way we just try to describe it. It is entirely an analogy. So else what you do? You just call anyone, call one person from the sofa who are actually relaxing. So they are not basically busy waiting. So here the equivalent of this will be, what is this? If, so again, what is the structure of the semaphore? We'll have some integer. It's not a mere boolean, it's now integer, and then q. Is that fine? So here what we do here, s dot x. What do I check here? S dot x is s dot x is, we can call it as we can specify it as count also. Okay, instead of x. So we can write here s dot count is greater than 0. Then s dot count is minus minus. Else what I do? So this means what? If we find that none of the lights are glowing, then you have to sit and relax in the sofa. So it is basically s dot q dot insert. Is that fine? Is that fine?
Yes, sir.
Yes, sir.
Yes, sir.
So the only thing is, the only change is now this is the resource type R, and these are the number of units. So resource type has got 3 units here. Okay, and that's why you are using, so this integer variable that keeps track, so it can move up to 3. Okay, so you have to initialize this value. So if you have got semaphore s s declared, and s dot count, you have to initialize it to 3. So it's like when you in the morning, early morning, when the shopkeeper or the booth owner opens his booth, he will switch on all the lights. That's all. So he will basically, this is the initial condition, initialization, right? Now throughout the day, this process is so this is the operations that customers actually perform. So VS, what is the VS now? The VS is if the S dot Q is empty, is if it is empty, then what we do, S dot count plus plus. Instead of setting it to 1, you basically increment one light. Else what you do? Else you delete one process from the queue. Is that okay? Is that okay? Hello?
Yes, sir.
So the first one here. So what the semaphore is actually trying to do? What the variable in the semaphore is trying to do? The value contained in it, what it actually signifies? What is the significance of that? Physical significance? It signals what? It signals if its value is 1 or 2. What does it mean?
Signal,
Hello?
availability.
Yes, it is a resource availability. How many units are still available for use, right? So when it is 0, definitely none are available. So can it take negative values? Can it take negative values?
No.
No, sir.
No. So that's why a semaphore is a shared construct which consists of a non-negative integer variable, say it is count or x, whatever, and a queue associated with it to track the waiting processes. And the variable can be subjected to, the semaphore variable, to only two atomic or indivisible operations, which is wait and signal, P and V. Now this is very significant. It is atomic. So the thing is, what is strikingly different from so you say that we have got the logic, we have got what P should be doing and V should be doing. So we don't need any operating system support, right? But this is not the case. So this whole operation. So the only thing to note is this whole operation of when you call PS, when you call here PS, this whole operation of execution of P is atomic, is indivisible, in the sense when it gets executed, you can see that P consists of so many steps. So it consists of several machine cycles, but in between those machine cycles, the operating system will guarantee that no timer interrupt also will occur. So there will be no preemption, there will be no interrupts that will be addressed or coming. Got the point? And this is the main point to note. So these P and V operations are treated or are considered to be atomic, and which is ensured by the operating system. That's why operating system support to make it. Otherwise, you found that a simple x equals to x plus 5 is not atomic. So how can we expect that the entire operation that is actually performed in the P, inside the P or inside the V, which consists of so many steps, how can they be atomic? But this is where the role of operating system comes, and the OS ensures that these are atomic. Got my point? So this is the point to be noted. And how it actually ensures the atomicity of this, so that will that I'll discuss sometime later. It uses a very special instruction called test and set, which is provided by the hardware, by the microprocessor hardware. In fact, that is the reason you cannot probably implement semaphore in a 8085 microprocessor, because it doesn't have that particular special instruction. Okay, using that special instruction, machine level instruction, this P and V is actually implemented by the operating system, and that is used by a user process or application to ensure say consistent access. So before I end this class, so this is when the semaphore takes 0 and 1, it is just controlling access to a resource which has got one unit. This is called binary semaphore, because the integer value can take binary values, and the second one where the integer value can take multiple I mean more than one values, I mean greater than one, this is called general semaphore. Okay. So this is the difference between binary and general semaphore. And the thing is, when this policy of who should be awakened up, if it is FIFO or whatever, if it is this policy is clearly mentioned, this is called a strong semaphore, and if it is not mentioned clearly, this is called a weak semaphore. Generally, we will deal with strong semaphores in our codes, where the policy is default and it is known to us that it is FCFS. So it will actually maintain a queue, but instead of a queue, we could have used a priority queue also. So we are not considering those kind of semaphores. So we'll be considering in our examples, in our while solving classical problems, both binary semaphore and general semaphore, at which are considered to be strong semaphores. Okay. So the point is, if during the wait time, if the process need to wait, it will not be a blocking wait. It will be relaxing. So it will be basically suspended, and but it will be waiting. So this is the point, and these P and V, these instructions are treated to be atomic. So this much for this class. In the next class, we'll see the reader writer problem and other problems. There will be 3-4 classical problems. We'll try to define the problem and try to solve it using semaphores. So you can, if possible, you can go through the reader writer problem and the sleeping barber problem. And we'll see that how binary and general semaphore together work to come up with a solution. Okay. So do you have any questions from this class? Any questions from this class? Hello?
No, sir.
Okay. So I'll pass on the videos for both the classes today. And the next class will be on Friday, first half, 12. Okay, thank you. I'm leaving.